Imagine a weapon that doesn't just fly faster than a bullet, faster than a jet, but faster than almost anything humans have ever engineered, moving at speeds greater than Mach 5, weaving through the atmosphere with precision, and striking before defenses even know what happened. This is the world of the Hypersonic Glide Vehicle, a technology that is rapidly transforming modern military strategy and redefining global power balance. A hypersonic glide vehicle, often called an HGV, is a maneuverable warhead that travels at hypersonic speeds after being launched into the upper atmosphere by a rocket. Unlike traditional ballistic missiles that follow a predictable arc into space and back down, an HGV separates from its booster and then glides along the edge of space, using aerodynamic lift to maneuver unpredictably toward its target. This combination of extreme speed and maneuverability makes it one of the most challenging threats for existing missile defense systems. To understand why hypersonic glide vehicles are so significant, we first need to understand what hypersonic really means. Hypersonic speed is defined as anything above Mach 5, 5 times the speed of sound. At sea level, that's over 6,000 kilometers per hour. Many hypersonic glide vehicles are believed to travel at Mach 10, Mach 15, or even faster. At these speeds, the physics of flight changes dramatically. Air doesn't behave normally. It compresses, heats up, and creates extreme temperatures around the vehicle. The outer surface can reach thousands of degrees Celsius, requiring advanced heat-resistant materials just to survive the journey. The journey of a hypersonic glide vehicle begins with a rocket launch, similar to a ballistic missile. The booster rocket propels the vehicle high into the atmosphere, often near the edge of space. Once it reaches the correct altitude and velocity, the glide vehicle separates. This is where the difference becomes critical. Instead of following a simple downward arc, the vehicle dips back into the atmosphere and begins gliding at hypersonic speed. Because it stays within the atmosphere and can change direction mid-flight, tracking and intercepting it becomes incredibly difficult. Traditional missile defense systems are designed around predicting trajectories. Ballistic missiles follow relatively fixed paths, allowing radar systems to calculate their impact points and intercept them. But a hypersonic glide vehicle doesn't cooperate. It can shift course laterally, change altitude, and approach from unexpected angles. This unpredictability compresses reaction time for defenders to just minutes, sometimes even seconds. Countries around the world have recognized the strategic value of this technology. The United States has been developing hypersonic programs such as the AGM-183 ARRW and the conventional prompt strike system. Russia has deployed the Avangard hypersonic glide vehicle, claiming it can reach speeds of Mach 20 and evade all current missile defenses. China has tested its DF-17 missile system, which carries an HGV and is designed for regional and potentially global strike capability. Each of these systems represents a major investment in next-generation warfare. The Avangard system, for example, is mounted on an intercontinental ballistic missile. After launch, it detaches and glides at hypersonic speeds toward its target, capable of carrying either conventional or nuclear payloads. Its extreme maneuverability is designed specifically to bypass advanced missile shields. Similarly, China's DF-17 combines a medium-range ballistic missile with a hypersonic glide vehicle, giving it the ability to strike targets within the Asia-Pacific region with high speed and precision. One of the key advantages of hypersonic glide vehicles is their flexibility in payload. They can carry conventional warheads for precision strikes against high-value military targets, or nuclear warheads for strategic deterrence. This dual capability raises significant concerns in global security. If a country detects a hypersonic launch, it may not immediately know whether the payload is conventional or nuclear. That uncertainty increases the risk of miscalculation and escalation during a crisis. Another critical factor is detection. Because HGVs travel at lower altitudes than ballistic missiles, they can fly beneath some radar coverage areas. Ground-based radars are often limited by the curvature of the Earth. Space-based sensors can help detect launches, but tracking a maneuvering hypersonic vehicle throughout its glide phase remains technologically challenging. This has led to a new race in early warning systems and space-based tracking networks. The engineering behind hypersonic glide vehicles is extraordinary. At Mach 10 or higher, Friction with the atmosphere generates plasma, a superheated ionized gas, around the vehicle. This plasma can interfere with communications and guidance systems. Scientists and engineers must design materials that withstand extreme heat, guidance systems that function despite signal disruption, and control surfaces that remain effective at hypersonic speeds. Every component must survive enormous mechanical stress and thermal pressure. Materials science plays a crucial role. Advanced composites, carbon-carbon materials, and specialized heat-resistant alloys are used to protect the vehicle. Some designs incorporate ablative coatings that gradually burn away to dissipate heat, similar to spacecraft re-entering Earth's atmosphere. Without these innovations, sustained hypersonic flight would be impossible. The strategic implications of hypersonic glide vehicles extend far beyond technology. For decades, nuclear deterrence was built around the concept of mutually assured destruction. Ballistic missiles provided predictable warning times and established defense postures. Hypersonic weapons shorten that warning window dramatically. Decision makers may have far less time to respond, increasing pressure during high-stakes situations. Some analysts argue that hypersonic weapons could destabilize global security by encouraging preemptive strategies. Others believe they simply represent the next evolution in military technology, similar to the introduction of stealth aircraft or precision-guided munitions. What is certain is that major powers are investing billions of dollars in research, testing, and deployment. It's important to distinguish hypersonic glide vehicles from hypersonic cruise missiles. While both travel at hypersonic speeds, cruise missiles use scramjet engines to sustain powered flight within the atmosphere. Glide vehicles, on the other hand, rely on initial rocket boost and then unpowered aerodynamic gliding. This difference affects range, trajectory, and potential mission profiles. Testing hypersonic systems is complex and expensive. Each launch requires precise timing, telemetry tracking, and advanced measurement systems. Failures are common in early development stages due to the extreme conditions involved. Yet with each test, engineers refine designs, improve reliability, and push the limits of speed and control. The global hypersonic race is not limited to the United States, Russia, and China. Other nations, including India, France, and Australia, are also investing in hypersonic research programs. International collaboration and competition are both shaping the future of this technology. The emergence of hypersonic weapons is prompting discussions about new arms control agreements, though no comprehensive treaty currently limits their development. From a military doctrine perspective, hypersonic glide vehicles offer the potential for rapid global strike, the ability to hit a target anywhere on Earth within a very short time frame. This capability could be used to neutralize critical infrastructure, command centers, or time-sensitive targets. However, such power also demands careful policy decisions to prevent escalation and unintended consequences. Beyond military applications, research into hypersonic flight contributes to aerospace innovation. Advances in heat-resistant materials, aerodynamic modeling, and high-speed propulsion may eventually influence civilian space travel and high-speed transport concepts. Historically, military research has often led to breakthroughs that benefit broader industries. As we look to the future, the question is not whether hypersonic glide vehicles will shape global security, they already are. The real question is how nations will adapt. Will new defensive systems emerge that can track and intercept these high-speed threats? Will diplomatic efforts lead to new agreements regulating their deployment? Or will the race for speed continue to accelerate? The hypersonic glide vehicle represents more than just a faster missile. It symbolizes a shift in the balance between offense and defense, between detection and evasion, between reaction time and decision-making. In an era where seconds can define outcomes, speed has become power. In the skies above, where the atmosphere thins and the earth curves beneath, these vehicles glide at unimaginable velocity, reshaping the landscape of modern warfare. The hypersonic age is not a distant future concept, it is unfolding now, redefining strategy, technology, and the very nature of deterrence in the 21st century.